Hi friends, in this video let us learn about current voltage characteristics of MOSFET in enhancement mode. Right, so you see the curve is drawn between VDS versus ID for various value of VGS. These characteristics I can call as drain characteristics because it is involving drain parameter. Right, so drain characteristics or VDS or current voltage characteristics both are same only. Okay, so from this what we understand, let us see. Right, so you take this one here, you see V threshold. V threshold is 2 volt. We learned from the operation of the NMOS when VGS is less than V threshold, what will happen in NMOS? NMOS will not conduct allow current flow, right? So ideally, when gate to source voltage is less than threshold volt, the drain current will be zero ideally. But here we have put some drain current. It is not exactly zero. It is some 0.5 microampere and nanoampere, like that. It will be very small value. But in practice, it is very small current flows, very small ID. What is the reason? Because due to the thermally generated electrons in the p-type substrate. The reason is current flows due to thermally generated electrons. Thermally generated electrons in p-type body. Right? So we know n-type mass will be like this. So this is n, this is p-type substrate. Here we have n plus region, here we have n plus region. Oxide, metal, source, gate, this is drain terminal, right? So what we understand, when VGS is less than VT, we learned, right? ID is equal to 0. Drain current will not flow because the channel is occupied by P. It's a body, P-type body. So electron cannot flow through this. But there will be some minor current will flow because it is a p-type semiconductor. We know in p-type semiconductor there will be a minority carrier flows due to the thermally generated electrons. So because of that thermally generated electrons, some current flows between the source and the drain. That is very small value. That is the reason we are having the curve starting from here, not exactly this yellow color, right? So ideally it should be ID is equal to 0, but practically it is having some small value. Okay, fine. Right, so here you see when you increase the VDS, from this we are understanding when VDS increases, ID increases. When you go from here, initially it is 0, when VDS is increased, ID is also increased. At one point they become constant value. That point is known as VDS saturation. So where it is becoming saturated at this point. Here it is becoming saturation at this point. Here it is becoming saturation at this point. What is the reason? We know VDS saturation is equal to VGS minus VT. Right? So when VGS decreases, you can see when VGS decreases, VD sat will also decrease. So that's why when VGS goes from 6 to 5 and 5 to 4, what will happen? VDS, this is VDS saturation point that is decreasing. So I can link all the points like this. So it will be like a parabolic. Exactly it will be like this. So here I am not drawing properly. So it will be curved like this. So whatever the region beyond that, this region, whatever the things coming beyond this curve, those things are called saturation region because their current is independent of voltage. So this region is saturation region. This region behind us, this is called triode region or non-saturation region. Here you see there is no current flow IDAD, so this region we can call it as cutoff region. So these are all the three regions of operation in the what you call NMOS transistor, right? So in each region we have a current equation. Let us see all the things now. Okay, so now we will see that. So you see why it is called saturation. When VDS increases beyond the certain value, that is VDS at. This point is VDS at 1. That is the shim 1. This is VDS at 2, like that, right? So it is VDS. So if we connect all the points, whatever the things coming beyond that, here that is saturation. Here the current is increasing linearly. That is called a triode or non-saturation or linear region. Okay. Fine. So next what we have to understand, in all the region we have current equation. The derivation is not important for us, so let us write the current equation, right? So first we define what is saturation region. The saturation region is one where VDS is greater than VDS sat. So that is the first point. In saturation region, VDS is greater than VDS sat. That is equal to what? We know VGS minus VT. So simply in saturation region, VDS must be greater than VDS sat, or simply VDS must be greater than VGS minus VT. Second, in saturation region, ID is constant, right? And independent of VDS. Okay, so in saturation region, the equation for current is ID is equal, this is very important equation. ID is equal to Kn VGS minus VT squared. N is for NMOS. Okay, right. So what is Kn? Kn is given by 1 by 2 mu n COX W by N. So here what is mu? Mobility of electron. Okay, so and this one COX. COX is nothing but oxide capacitor. Oxide capacitor per unit area. Okay, so that is given by, let us see all the things, with W is width and this is length, width by length ratio I can call. So what is Kn? It is nothing but a conduction parameter. Conduction parameter for NMOS. Okay, so that is another important point we have to remember. Conduction. This is width of the channel, length of the channel. Okay, so right. Fine. Conduction parameter, mobility of electron. So here oxide capacitance COX is given by epsilon OX divided by TOX. Okay, so what is EOX? EOX is oxide permittivity. Oxide permittivity, and this is oxide thickness. Okay, so for silicon, this we have to remember. For silicon, EOX is equal to 3.9 into 8.854 into 10 power minus 14 farad per centimeter. Don't forget, right? So it is 3.9 into 8.5. So 8.854 into 10 power minus 4. It is for only silicon, right? Okay. So you see from this conduction parameter, we can understand one important news. So what is the information we are getting from this? It is mu n is, what is the, it is a electrical property. So Kn is the function of mu n. Mobility is electrical property. So Kn depends on electrical property. W by L C is, that is a, and Cn is, C is also a electrical property. W by L is a physical property. So or geometry property. So it is both Kn, conduction parameter, is a depends on electrical property and geometry property of the device. Okay, so that is another point. Then we will define Kn in terms of short form, still Kn dash 1 by 2 W by L. So this implies Kn dash is equal to mu n COX. This is called the process conduction parameter. Right, so this is process conduction parameter. Right, so I can write Kn is equal to Kn dash W by 2L. Right, so this only we should remember. These are all useful to solve the problems. Okay, next, what is the thing we know? What is Kn? Kn unit. Kn is 1 by 2 W by L mu n COX. Right, this is the form. What is the unit of W? It will be in normally centimeter. It will length is also in centimeter. Right, this is mobility, centimeter square per volt second. COX, that can be written as EOX by TOX. EOX is nothing but farad per centimeter. TOX is thickness, it is nothing but centimeter. Right? So what will happen if you cancel all the things? What we get is centimeter square, this centimeter, centimeter out, centimeter, so it is centimeter, centimeter, centimeter square out. So what is the thing? It is farad by volt second, farad per coulomb, farad by volt second. So F is equal to C by V, capacitance, F farad, C by V. So it is volt second, volt to volt. So what is coulomb per second? Ampere. It is volt square. Right? So in this way we can find, right, it is centimeter square by volt second, right? So you see this is C, V, C by V. Okay, so in this way we can find out Kn unit is ampere per volt square. So unit of Kn is ampere per volt square. Right, so next we will find a current for triode region or non-saturation region. For that, current is given by ID is equal to Kn 2 into VGS minus VT. VDS, VT means VTN only, VDS square. Right, here you see we can find ID is depending on VDS. It is mapping, right? See, ID is a function of VDS. That's what we have studied in the curve also. When VDS vary, ID vary in the triode region. In the curve we see. Okay, so in triode region, when VDS vary, ID varies. Whereas in saturation region, you can see that, you see what is the formula for current in saturation? ID is independent of VDS. You see, ID is independent. That's what we have seen in the curve also. When VDS changes, ID won't change. Fine. So when VDS beyond this curve, you see when VDS changes, ID is constant only. It won't change. ID is independent of the curve. So this is one important point to be noted. And last one is in MOSFET, there is no input characteristics. MOSFET, no input characteristics. What is the reason? Because in MOSFET, what is gate current? IG0. Right? We are not getting any input current, so there is no input characteristics. Right? That is another important point to be noted. That's all about this session. If you have any doubt, ask me in doubt section or comment section. I will clarify. Thank you.